Okay, we're good to go. So Alfredo will talk about color kinematics, lessons from celestial holography.
All right, I assume you can all hear me. First of all, let me thank the organizers for uh, putting together this nice conference. I'm very sorry, and I have to apologize that I haven't been able to join you this time. But I look forward, of course, to seeing you all in person. This time I would like to tell you about some project I've been thinking on recently, related to color kinematics and celestial holography. But it's rather part of a more general picture that seems to provide an alternative framework to how these results, how recent results in celestial holography are can be interpreted, and what's the sort of way to think of the reformulation of the S matrix per se. The main motivation, I guess, the main motivation is, of course, there's a very simple relation in certain cases between gravity and gauge theory. And we may want to explore whether that can teach us about celestial holography, although in this sort of project, it seems to be more of the other way around. It seems that celestial holography sort of informs what's the sort of appropriate way to do color kinematics and so on. But of course, there is some interplay. So let me just give you the sort of micro outline of the talk. The first part is essentially motivation and explanation of what's the color theory that I'm talking about. And the second part is more technical. So I dubbed it how sausages are made. And it involves certain topics such as quantum groups and twistor theory and related topics to integrability and so on. But I guess most of the message would be condensed in the first part. So if you I understand that it's very late there. It's late evening, so if you want to go take a break in the middle, you're welcome to do it. So first, let me start by just giving you a very overall broad picture of why are we doing color kinematics in general, or what's cool about this. I guess for me, it's mostly that the string theory taught us many lessons over the years since the 90s. And we have learned a lot about quantum gravity and its relation to gauge theory. But sometimes some of these lessons don't need to don't seem to require string theory at all. So ADS-CFT, even though it was derived as a strong weak duality between string theory and super-Young Mills, we know that many aspects of holography actually don't rely on string theory. In fact, there are lower dimensional versions of holography, such as 1D or 2D SYK models. There's KRCFT, there's near horizon holography, and so on. And all of these developments seems to point towards the fact that holography is really an independent thing. We have learned about field theory after the green shards cancellation. We learned that even in field theory, there are very interesting ways in which anomalies can be canceled, even though this was first, of course, inspired by type 1 superstrings. And one of the lessons that I will be focusing on this talk is the color kinematics duality. So this was also derived from string theory. And it came in the form of KLT relations, which essentially just relate closed strings to open strings. Their path integrals are related in a very simple way. And the outcome of this relation between path integrals is essentially just amplitudes being related on both sides. So we say that gravitational amplitudes or closed string amplitudes are the square of open string amplitudes. But we understand now that this is part of a more general law that doesn't require us to talk about KLT, and in fact, it has many sort of classical, even in general relativity, we can see aspects of color kinematics. And in that sense, it's sort of an independent field. And of course, there is celestial holography, which shares many commonalities with sigma model constructions that are used in string theory, but of course, as we know, our 2D theories live in the celestial sphere rather than in the worldsheet. So this wouldn't preclude, of course, the possibility that there is a direct connection between the two via something such as the scattering equations or the Amplitudes framework. Okay, so in this talk, we will study the interplay between celestial holography and color kinematics. So what is color kinematics? Let me just rewind a little bit. So the color kinematics duality is the fact that gravity amplitudes, in many cases, can be obtained from gauge theory amplitudes under the replacements of color factors by kinematic factors. Okay, and this was first pointed out in this particular version by Björn, Carrasco, and Johansson. And the simplest sort of quintessential form of this duality is the 4.3 level amplitude in Yang-Mills theory. So if you just do a Feynman diamond computation in some particular gauge, you can always write your amplitude in this form. Okay, so you can see my pointer. These C's are color factors. So they obey a certain relation. They are essentially structure constants, and N are kinematic numerators. So you have 3 diagrams, 3 color factors. You, after you worked out, it turns out that the color structure constants satisfy a very simple identity that tells you that there's a Lie algebra underlying the Yang-Mills amplitude, and that is called the Jacobi identity, and it's actually required for correct factorization and sort of crossing symmetry properties of this amplitude. So you can write a consistent quantum field theory if you don't have a Lie algebra. And in fact, after you write it in this form, you will find, to your surprise, that the numerators, these quantities here, and that depend on kinematics and polarization vectors, actually satisfy a very similar looking identity that we call kinematic Jacobi identity. And so the kinematic Jacobi identity is sort of kinematic avatar of the sort of color structure. And moreover, if you actually take your color structure constants and replace them by kinematic factors so that you get them squared, you get twice as many polarization vectors, you have a spin 2 theory. It happens to be just gravity. So this is a very general fact. I'm giving you just a more sort of simple case, but it actually goes beyond tree level. It goes to loop, and it goes to loop level, and it can actually be applied in many general sort of classical systems as well. And so the key point here is this replacement, right? So I'm taking C's and I'm replacing them by N's. Okay, so the immediate question you would ask, oh, sorry, is there a question? All right. Please stop me if you have any questions, of course. But here my buddies have some questions, of course, and one of the first questions is whether there's an interpretation for the kinematic Jacobi identity, whether it pinpoints some underlying symmetry algebra that's completely pertaining kinematics rather than Yang-Mills sort of color algebra. So you can take 2 stances. One is sort of an optimistic position, and the other one is a very pessimistic one. In the optimistic case, you would think that gravity is a very simple theory because it's related to a color theory, right? So the kinematic Jacobi identity is nothing but the avatar of a color theory. And so every technique that you develop for color theories, such as, we know about, for instance, the Park-Taylor amplitudes, we know about the twistor string formalism that was developed for super Yang-Mills, we know about Yangian symmetry. All those things could go into gravity if you sort of take this optimistic perspective. But the pessimistic one would tell you, well, this is just some kind of accident, self-dual gravity. It's kind of simple, it's integral, and so on. Maybe MHV amplitudes happen to have some simplicity. The one that I just showed you actually is an MHV amplitude in 4 dimensions. Or perhaps it's that gauge theories are way more complicated, or maybe we haven't really understood fully in detail what super Yang-Mills is. We know that there is Yangian symmetry, but we don't know whether it's integrable or not. We believe it's integrable, but Yangian symmetry is not really as simple as we thought. So we cannot really solve for the S matrix as face value. So there are sort of 2 perspectives on this. So clues to answer this question actually come from soft-dual gravity, as I just mentioned, which were studied long ago, of course, by Penrose and Ward. But sort of the key point that sort of motivated this work was made here by Monteiro and O'Connell, and it's the fact that all these kinematic Jacobi identities seem to arise from extended symmetries of soft-dual gravity, right? So soft-dual gravity, being an integral system, actually have an extended symmetry algebra, and that plays a role. It can be interpreted as some algebra of area per 7 diffeomorphisms, which is W infinity and so on. So we can really sort of link the kinematic side of gravity to a sort of a gauge symmetry. But so this is also being further developed in these recent papers. But you may want to explore this in more generality than just soft-dual sectors. And sort of evidence for that, again, comes from the fact that there is Youngian symmetry, which is completely general in super Yang-Mills. There are positive geometry descriptions of super Yang-Mills. There is amplitude with some loop dualities, and all these things are general in the sense that they don't require soft-duality at any step. So it may be that actually these non-trivial statements about super Yang-Mills actually have an avatar in gravity. So that brings me to sort of the second point that I want to make, is that there are very general sort of features of gravity that don't rely on soft-dual conditions that are also, pointing towards the fact that there is a connection between a color theory and a gravity theory. Of course, the first is the ABS-CFT correspondence, which we know we can compute correlation functions in CFT, and they are related to supergravity amplitudes. And so we can essentially aim to take a flat space limit to define the S matrix from the CFT. There's also the fact that there's avatars of Youngian symmetry. So even though you would think that super Yang-Mills has Youngian symmetry, but supergravity doesn't have, we know that supergravity has many features of Youngian symmetry. If you compute loop integrals, you will find that they are given in terms of essentially boxes. So this is what's called the no triangle hypothesis, and this is essentially, a feature of an avatar of dual conformal symmetry. So even in supergravity, you will find that there is some underlying constraint that we don't really fully understand. The classical aspects of gravity also have some integral properties. These are more well known and famously explored as hidden symmetries, as integrability of geodesic equations of motion. The two-body problem has some effective one-body description. So all these things actually end up related to amplitudes, and sort of hidden symmetries of the S matrix. And actually, one of the simplest instances of that is this very interesting relation between quasi-normal modes and Seiberg-Witten theory, which I encourage you to look at if you haven't already. Of course, there's Penrose nonlinear gravity, the graviton theory, which also tells us that we can sort of perturb around soft-dual fields and consider soft-dual backgrounds, and so try to derive more general helicity sectors starting from this integral sector. So that's very much related to Ward's old conjecture about generic integral Hamiltonians being obtained by reduction of soft-dual systems. But moreover, we know that in recent years, we have observed asymptotic symmetries, which are essentially an infinite tower of symmetries that appear in the scattering problem. So all these sort of interconnected topics sort of point towards the fact that there's an integral structure in gravity, and color kinematics seems to be a right sort of a promising path to address it, right? So I'm sorry if I'm being sort of very broad, I wanted to emphasize more generally why is the color kinematic structure sort of in the core of integrability, or why we expect it to be. But maybe to be more precise, let me just outline what I'm gonna discuss in this talk, which is an aspect of integrability, which is that we are gonna argue that perturbative scattering amplitudes are in a sense controlled by an infinite set of conserved charges, and that these charges organize into a W1 plus infinity hierarchy, which was recently observed, if not sort of inspired by constructions in celestial CFT, but also from twistor space. So in the celestial CFT language, this was pointed out in these works. But there's of course a very parallel story in terms of surface charges in asymptotically sized spacetimes, which was nicely elaborated in this paper. And of course, there's a connection with twistor holography in the case of gauge theory. So there's a nice sort of organization principle given by W1 plus infinity that we address and we try to make it explicit in celestial CFT, but it points towards the fact that because you have an infinite constraint on the amplitude, the fact that the amplitude might be determined using these generators. Okay, so the point I'm gonna make in this talk is that from the 2D holographic world, sort of in the celestial sphere, the W1 plus infinity hierarchy can be recast into an infinite set of 2D cosmic currents, which correspond to the gauge group UN. And the U instead of SUN is very important because it's W1 plus infinity and not W infinity. So that's why there is no S here, where the number of colors tends to infinity. So it's a large N correspondence. And this is related to the gravitational CFT or celestial CFT via the color kinematics correspondence. So just to give you a sort of an overall map, there is for the gravity and the perturbative scattering amplitudes are obtained by color kinematics, as I just showed you in the first slide, using this replacement of kinematic structure, the structure constants by kinematic structure constants. All right. So you can start from super young mills, do this replacement, and get to 4D gravity. In the sort of 2D world, what we have is the 2D gravitational CFT, which carries W1 plus infinity symmetry. And that can be obtained by starting from a 2D community theory of currents. For this color group, actually, it should be SUN. Sorry, it should be UN, not SUN. And then taking N to infinity. So this N to infinity is sort of the color kinematic replacement in this case. And this idea of using large N limit to obtain gravity is not new. Even before holography, which is the most famous example, of course, it was pointed out in these papers that large N sort of Cat-Moody or Wessel-Witten models can be reduced into software gravity models. Although these papers are a little obscure to me, they deal with twistor actions and so on. I presume it's the very same. It's the very same construction. Although I haven't really explored them in detail. Okay, so rather than derive explicitly how the correspondence works, which I'm gonna do in the sort of second part of the talk, let me just give you a sort of flavor of why this should be true and how will it work in general. Just by looking at the leading order, which is in the soft expansion is just the leading soft graviton. In the CFT language, we define it as the residue of a generic sort of positive helicity graviton operator, which has helicity 2, but weight delta, and then we take the delta equals 1 residue. So this is the more familiar version of the leading graviton. And in momentum space, which is sort of more convenient, we can take this sort of primary depending on the energy and the space sort of celestial sphere coordinates, set and set bar. And the Weinberg-Sub theorem of the S matrix actually can be recast in this form, where you have essentially set bars upstairs and sets downstairs. All right, so from here, the first thing you notice is that H1, the leading graviton, must be weight 3/2 minus 1/2. And the reason for that in these coordinates is that omega is an energy density, so it carries weight 1/2, 1/2. It doesn't carry spin, but it's a density. And Z has weight 1, Z bar has weight -1, and so you essentially add them up and you get 3/2 minus 1/2, right? But something you can do is you can do a sort of little group transformation where instead of having omega as an energy density, you sort of rescale it and you send it all to lambda tilde. All right, so this is not the sort of homogeneous version of the correspondence that we usually do. It's essentially just sending all the energy dependence to lambda tilde. When you do that, there's a little group scaling in both of these factors. And the end result is, as you might have seen before, essentially you can replace this by a square bracket. Omega Z bar times the other omega actually become a square bracket of 1, 2, which are lambda tilde spinors. And what we're going to do is we're going to provide evidence, very simple evidence that 1, 2 should be thought as a color structure constant rather than as a sort of independent worldsheet variable or celestial sphere coordinate. And in fact, it's very explicit why it has to be, because it actually corresponds to SU infinity and the sort of, usual sort of relations that this bracket satisfies are actually the Jacobi identities of SU is infinity. And we have that if we have this color structure constant upstairs, which absorbs the energy dependence, the first thing you notice is that downstairs we only have weight 1 denominator. So actually that turns H1 in this frame to weight 1,0. So it becomes completely holomorphic just because you have reabsorbed the Z bar dependence into this sort of color structure. So that gives you a hint of why you should think of H1 as a Kac-Moody curve. Actually, if this actually corresponded to a structure constant, this being a holomorphic OPE would actually match the OPE you get from Kac-Moody currents acting in the adjoint representation. And you can do the same, although it's more intricate for all subliving gravitons in this framework. Although I'm going to discuss that a little later. All right. So why should we actually think of this as a structure constant? Well, the first piece of evidence for that comes from what we call in this paper the chiral OPE block, which is nothing but an integral form of presumming all the descendants in the celestial CFT OPE. So if you start from your leading order and then you act with sort of SL2R right beta sort of generators, or sorry, SL2R right generators, just by themselves, you will find that the whole tower of descendants actually can be resummed into this integral form. And there are many ways to derive this, but one is BCFW, there's collinear limits and so on. But it's still curious that you can only resum sort of the right movers, but not the left ones. So that hints you that at least the right movers have to be obeying sort of underlying symmetries because they are completely rigid, in contrast with the left movers, in which case we only have like the leading order. So this suggests that there is a higher symmetry representation at play, which is essentially the W symmetry. But the sort of trivial way to see it is just recasting this OPE in the sort of momentum basis, which I just explained to you. Essentially, just writing lambda tilde as omega and 1 Z bar. If you recast this OPE block in the momentum basis, it takes also an integral form, except that the sort of structure constant actually diagonalizes the OPE, and as it should be because it's a momentum agent state. But the key point is that this structure constant is actually an structure constant. It actually corresponds to SUN, as I will show in a second. Now you can see that both sort of forms of the OPE are completely determined for the right movers, but are only leading order in the left movers. Okay, so what's with these structure constants that have a delta function and actually correspond to SU infinity? First, they immediately imply that we can recast this whole tower of descendants in terms of just Catmull currents. This is simply because once you absorb the holomorphic, the sort of anti-holomorphic dependence, all you have is just a pole in terms of set 1, 2, and that sort of points towards the fact that this G here can be thought of just Catmull acting on some field which is in the adjoint representation. And the second fact that it implies is, if you look at the associativity of the OP I just showed, is that there is some there is a Jacobi identity for the kinematic part. So Z bar, when combined with omega, the energy actually satisfy a very simple Jacobi identity. That is nothing but the trivial sort of Jacobi identity that we write usually in terms of spinors, which is nothing but 1, 2, 3, 4 plus sort of cyclic combinations actually equals 0. So it's the vanilla, linear dependence that 3 spinors have in 2 dimensions. And this is 0 under the support of the overall delta function for momentum conservation, which is also part of the structure constant. So that tells you that the associativity of the OPE, which was something that was not required to start with. We started with collinear singularities or whatever method we used to derive the OPE in celestial CFT, actually corresponds to the Jacobi identity of a Lie algebra. Otherwise, it wouldn't have been sort of Catmull theory. It would have been something else. Okay, in this framework, we need to include negative helicity operators. These are very easy to include by essentially incorporating an auxiliary scalar field. So we have seen some aspects of this in the Costello-Paquet construction, but there is also Bean was just telling us about how to incorporate negative helicity gravitons. In this sort of language, because we are sort of integrating out the right movers, negative helicity gravitons are just scalar fields, but you can still allow for a contact term. You can still allow for a coupling, essentially because we're working on sort of the Lorentzian CFT rather than the Euclidean one. So if you allow for this coupling, you will find essentially that you can compute 3-point amplitude very easily just using the OPE of 2 gravitons or 2 gravitons on a scalar, or you can use graviton scalar and then hit it with the other graviton. It doesn't matter which order you do, as long as you accept that the pole in the OPE is related to a delta function. The computation is completely exact and is kind of trivial to do. Now, the reason for this correspondence here is that essentially we don't have any other singularities at 3 points. So we can replace, because there is no other singularities, we can replace the delta function by a pole if we assume that there is some contour prescription for dealing with a pole. So once we do that, the 3-point amplitude, of course, looks like this. If you recall that the structural constants actually have a delta function themselves, you will find 2 delta functions coming from color and 2 delta functions coming from the OP. And the Jacobian magically turns out to be just the 3-point MHV amplitude. Now, what that tells you is 2 things. So first, momentum conservation comes sort of emergent from the color structure and the sort of singularity structure. It tells you that the sort of antichiral part of the momentum conservation is just SUN theory, but the sort of chiral part is coming from the OP. That essentially implies that 4D momentum emerges sort of in a mixed fashion. And the second thing that it tells you is that even though we computed all these OPEs in a fixed helicity frame where we write lambda tilde omega 1 z bar is still something that makes sense for general little group transformations, because this Jacobian here actually transforms as it should under little group transformations of all of these primaries. So it's a sort of a different frame that we have to adopt to compute the OP, but once we compute it and we extract the Jacobian is exactly the amplitude, and it has the right little group transformation property.
So can you build up
Okay.
from that guy? I mean, like, are you making any assumption here? This isn't like this is full all of gravity, or like this isn't just self-dual, or?
So it's chiral in the sense that the currents here are chiral, they are holomorphic. The sort of negative helicity graviton is a contact term in the sense that it doesn't depend on Z bar. In the sense there is no Z bar, so all the non-trivial structure is encoded in the color structure constant. So, but this is 3-point MHV, so you won't distinguish between self-Boyle gravity or.
So just one dumb question. So I can have one helicity graviton of any energy, and then it's like I only have a conformally soft other helicity guy. Is that accurate, or that's not a accurate summary?
Right. Yeah, that's a good question. So I didn't emphasize enough that here lambda. Actually, this should be lambda tilde, by the way. Here lambda is completely generic, so we wrote lambda as omega 1 Z bar. And omega is not, it doesn't need to be small. It's completely general energy range. So this sort of coupling between the graviton of positive and negative helicity is actually what you would get from the color structure. This is nothing but delta AB if these are sort of two helicity Moody currents. So in a sense, the color structure completely captures, the coupling between positive and negative helicity gravitons at all energies. And this can be decomposed, of course, into omega prime, Z prime, Z bar prime. Is that answering your question, or?
I think so. I guess I'm wondering if from that 3-point function, which other amplitudes can you build up? Is it only ever MHV amplitudes, or?
Oh, okay, yeah. I'm gonna get to that point in a couple of slides. Yeah, sorry. I was just gonna mention the 3-point amplitude first, and then how to construct higher point amplitudes actually relies on a BCFW construct. Yeah, just hold that thought for a couple of slides, and we're gonna get back to higher points at some point. All right. So yeah, actually, so the first observation that occurs at higher points is even the 4-point amplitude is not a trivial construction. It actually reflects associativity. So suppose we want to compute the 1 minus amplitude, we usually would assume that that is 0 in gauge theory or in gravity. But it's actually not 0. What is 0 is the amplitude on the support of generic momenta. The sort of support of the amplitude is very degenerate, but it's not 0 identical. To get something that is 0, we have to sort of integrate over the momenta. So here that's reflected as some kind of contour integral that I'm not going to elaborate much on how it is done. But once you integrate over these contours, essentially you can find that the 3 terms that would contribute to this 1 minus amplitude would sort of conspire to give you exactly what you would call the Jacobi identity in this case. So here, each of these terms would have a color structure constant squared. In the kinematic language, each of these terms would correspond exactly to one of these terms. And the vanishing of the amplitude in this sort of degenerate support actually is equivalent to the Jacobi identity. So that's the first sort of constraint that we want to see. We want to see that the amplitude with 1 minus graviton vanishes. as I said, it doesn't really vanish identically, but it vanishes if you sort of take this contour information. This is a very general fact of 1 minus amplitudes. Actually, was pointed out first by Witten in the twistor string construction. But for generic momenta, of course, we don't usually care. So the fact that the vanishing of a 4-point amplitude implies associativity was also sort of emphasized in this paper by Spradlin and the group. And we believe that there is a very nice way of seeing this momentum space, which is completely equivalent to the usual sort of celestial CFT derivation of using associativity of the OP. All right, so that was sort of the outline of how would the correspondence between color theories and gravitational theories proceed. Now, the more technical stuff that I won't really go into much detail, but I will sort of outline the construction is essentially based on twistor theory, but also in what has been called quantum groups. There's a sense in which W, or at least the quantum version of W, is precisely a quantum algebra. It's not a Lie algebra. It simplifies a lot when you take n to infinity. So Wn as a quantum group is very far from being a Lie algebra. It's very nonlinear. When you take n to infinity, you can actually realize it in terms of linear operators. So that hints you that even for the classical case, you would like to take the large n limit rather than sticking with a generic n. So the simplest sort of realization of W when n is infinity is area preserving diffeomorphisms. I believe that most of us already are familiar with this representation, but I will just outline the sort of key formula, which is essentially this Poisson bracket. Once you take a space with 2 coordinates, it can be a torus or a plane. It doesn't matter up to central terms. The area preserving diffeomorphisms are an algebra under the Poisson bracket, and if you ask for them to be regular, that means they are just polynomials. So it's essentially the space of polynomials in these 2 variables. These are homogeneous polynomials that satisfy this Poisson algebra. So there's a very nice interpretation of what these mu coordinates are in terms of twistor variables. I'm not going to delve into those details. As I said, we'll be mostly thinking of the quantum group structure. So W historically was first defined as a classical limit of big W, which is the sort of large n limit of Wn. We know that Wn is an operator algebra for infinite number of spin fields. Actually, if we have a finite number of higher spin fields, as I said, we have these sort of quadratic and multilinear generators. Those are not realizing a Lie algebra or any affine algebra, so they are sort of very nonlinear. And we know that it simplifies only if we take the number of higher spin generators or their spin to be infinity. So this is very much what happens in the S matrix when we have, say, spin 5 halves or spin 3 generators. We have some problems with factorization and unitarity as 4 points. Those are easily or nicely solved by string theory when string theory incorporates all the possible higher spin, the full higher spin tower. So that's what simplifies the string theory amplitude. In this case, it's what simplifies the sort of quantum group structure of W. So another nice thing about W is that it has a Hopf algebra structure. Now, I wouldn't be mentioned this if it wasn't because that Hopf algebra is precisely what appears in the Youngian theory of supergiant mills. The only difference is that the Youngian theory associated to W is a Youngian of GA1 rather than SUN. So that tells you that there is some sort of color kinematics correspondence. So there are very interesting connections between that and the color structure. So here I'm going to outline this one, which is that if we take a quantum group for SUN, where we take n to infinity. N to infinity plays the role of a classical limit, and the result of that classical limit is essentially W. And the sort of simplest way to see that is using the framework that Hopf developed in the 80s. The reason for that is that Hopf was secretly working in momentum space, even though his construction doesn't mention momentum space at all, or twistor space or nothing like that. He was secretly doing the construction in this sort of two-dimensional torus, which is basically twistor space or a twistor fiber. So how that works is you start by quantizing the algebra that I just explained to you. The quantum version of that is, of course, the Heisenberg algebra. You can think of this being X and P, and there's a very natural sense in which this will be Goldstone modes because they are sort of they essentially correspond to X and P in the torus. And classically, as I just said, they correspond to twistor coordinates on a C2 plane, which is a fiber over the celestial sphere. We will consider the case where n is finite. So this you can consider for any sort of coupling. You should think of this coupling as being some quantum h bar. The large n limit corresponds to h bar to 0. So it would be some kind of classical limit. When n is finite, so the quantum version of that is that you will essentially find these conditions, which tells you that you're in a torus. You're essentially in a lattice, right? So there's a lattice. It has this sort of modular parameter. We call it tau, where q is e to the I tau. And what the parameter measures is the non-commutativity in this lattice. So if you have these group elements here, they don't commute unless n is infinity, in which case it becomes just a standard commutative plane.
Alfredo?
Yes.
It looks like those quantization, the torus conditions look like they break Lorentz invariance. Is that right?
So far there's no space-time picture. What you're probably referring to, I guess, is that there is an SL2R sort of transformation that mixes plus and minus. I guess that's what you mean.
That's right. Yeah. So
yeah, right.
Your commutation relations are covariant with respect to that, but your periodicity conditions, I'm not sure that they are.
Right. Yeah. I think you are completely right. Yes. Of course, we're going to take the large n limit and we're going to recover. We're quantizing a lattice, of course, and so the sort of symmetry group is an SL2 set rather than SL2R. After we take the large n limit, the lattice becomes unquantized, and so we recover the full continuous symmetry. Is that answering the question?
Well, maybe. I mean, people get very worried about having an emergent Lorentzian symmetry from quantizing a lattice, right? You can get emergent Euclidean symmetry. I don't know whether you can get emergent Kleinian symmetry, but I think there are theorems that say you can't get emergent Lorentz symmetry.
Right. I think the modular group here is it's not exactly the Lorentzian symmetry unless you take large n. I think in the large case, so essentially what happens is that tau doesn't need to be discrete. Tau here, let me just introduce tau, can be any sort of finite parameter. The reason I'm discussing the sort of discrete version of tau is because I want to make a connection to SUN. If there was a continuous version of SUN where n is non-integer, I wouldn't need to be doing this. So the only reason that we sort of fixed tau to be 4 pi over n is because we want to essentially connect this symmetry group acting on the lattice to SUN, which is sort of the color kinematic duality. But other than that, we can think of tau as being a completely generic a parameter. If tau is generic and non-integer, there is no quantization condition. Yeah. So the sort of color kinematic aspect of it comes when tau is 4 pi over n, in which case you get this n by n lattice. But I understand your concern, so we should discuss that more in detail. Okay. Just the point I want to make here is that as you take n to infinity, that's exactly taking q to 1, that makes it commutative, and so we get the full plane. And we recover, of course, from the commutator, we recover the Poisson structure. So even though Hub in his thesis actually didn't mention momentum space at all, this is exactly sort of the momentum space construction of SUN. To see that, as I said, we consider lambda living on an n by n lattice. The reason that we're going to consider lambda living on a lattice is because lambda is the conjugate to mu. So if mu satisfies these conditions, where sort of idempotent, you will have that lambda essentially is identified. It lives in an n by n lattice. So after you consider these sort of wave functions in the lattice, you will have n square generators. The sort of zero momentum generator, which is 0, 0, is the identity. So G 0, 0 is 1. If you discard that, you will have n square minus 1 generators that would actually give you an SUN basis. But for the purposes of connecting this to gravity, we actually want to have the identity. So I'm going to consider UN rather than SUN. So, of course, the problem is that if you want to realize SUN as finite n by n matrices, they are not really exponentials of these mu's, because mu's are always sort of infinite dimensional operators, right? Because they satisfy this Heisenberg algebra. So that's expected. We want to think of mu's as being Gaussian modes, and we know that Gaussian modes are not normalizable. So there's no reason for this mu to be actually well-defined operators. But the algebra actually works out if you consider the exponentials and you start doing sort of commutation relations with these G's. You can use the commutation relations for mu, and you'll find what's the algebra, even though it doesn't have a finite dimensional representation. So here I'm doing just that. So if you take two G's, there is this sort of Bernstein formula that tells you that you can essentially use Barker-Campbell-Hausdorff to multiply these operators. And if you take large L limit, it essentially looks like this. And what's important point is that here the momentum adds. Of course, you get the exponential times the other exponential, so you have the momentum. After you take the large L limit, the structure constant that survives the antisymmetrization is just this. And so you get essentially what is SUN in momentum basis, right? So even though we started with something that didn't have a finite dimensional representation, this actually has a finite dimensional n by n representation. And in fact, as we expect, agrees with the Poisson bracket of two exponentials, because it's essentially just a classical limit of this commutation relation. So once we are taking tau to 0, we are recovering the Poisson bracket. Okay, so that's, I guess, one of the yes.
Can you hear me? I'm not sure.
Yes.
Okay. Are you getting SUN or SLN, or what precisely are you getting? It looks like you're saying you're getting SUN.
if you discard the identity, you get SUN, right? Here I'm getting UN, right? These are the exact UN
Compact.
UN structure constants.
It's really the you're not going to see it from structure constants. You're getting the compact group, not the non-compact group. That's what I'm questioning about. Is it really SU or SL?
Oh, I see. So you're questioning whether it's SUN.
Because I can believe that you get emergent Euclidean symmetry. That's fine. That's just normal lattice stuff. Okay, you're doing it in an exotic way. I find it harder to believe that you get anything emergent in the other ones that restores, Lorentzian or Kleinian symmetry. And then the fact that you're only looking at finite dimensional reps also makes it seem like you're looking at compact groups. But I'd be nervous that, we know there are no momentum eigenstates in Euclidean signature for massless stuff. So that somehow I don't know. Just confused.
Yeah, I feel like I should refer that question to Hobbes' paper. I feel like his construction works very well, as you said. So he constructs this equivalence for actually general compact groups, as long as there is a killing form. There is a very simple map between group manifolds and this sort of spinors. I believe that we want to reproduce UN because UN has the identity. I don't think so. I don't think SUN is the algebra we want, because it doesn't have sort of the central term in W1 plus infinity.
Again, I don't mind whether it's UN or SUN. I'm happy with either of those. The question is whether it's those rather than SLN. Anything compact is fine. It's whether you're getting something that's non-compact, which I think is what you need if you're away from Euclidean signature.
Yeah, I understand the point. I'm not sure where the compact assumption is sort of given away. So far it's SUN, so far it's a compact group. These are essentially wave functions on a torus. So in the classical, right? So in the sort of classical limit, this is a torus. It's essentially compactified. So these are wave functions which are essentially exponential of the torus coordinates. So you can think of them as angles. In the quantum case, this is sort of the quantized version of the angles is the SUN generators. So far it's all compact. It's not, I don't believe it's SLN. So the concern whether we would violate the compactness assumption when we go to Kleinian signature, I think should play a role moving forward. But so far I'm not making that connection. But yeah, you should come back and ask me when I finish the sort of equivalence discussion. So far we're just discussing group theory. So I wanted to sort of give the overall picture because this is sort of the motivation that we're going to use to construct the amplitudes, but these are not the operators that we're going to use in that case. Although the operators might be even more intricate, so we want. So your question still applies, but not for this slide. That's what I'm saying. I'm not mentioning Kleinian space-time. Sorry, I cannot see the camera, but I think you are.
Oh, sorry. I'll be quiet. So carry on. Sorry.
Okay. No, that's very fine. So we should discuss that in detail. Although maybe we don't have time in this occasion. So let's move forward. I guess what's your name? Just to make sure I recognize. Oh, okay. Hi. Yeah, so I couldn't see the cameras. I was trying to guess who this was, but I kind of guessed that. So well, so far we have explained how the large n limit of SUN provides a realization of W. All right, so this essentially Hop did in his PhD thesis. After you take large, so the sort of size of the sort of n by n lattice is 1 over n. If you take large n, actually you can take sort of continuous n, and in which case there's no quintessential at all. You can recover R square or the torus. The resulting color algebra is two-dimensional because it's given by a lambda spinor. So it's parameterized by this momentum spinor. So this fact has been observed, you know, it has appeared in many contexts, but probably sort of color kinematic interpretation is very recent, and it has been used to constrain 2D integral models. So I refer you to these papers. I'm sure there are more instances of this, but what we want to do is, of course, we want to do something 4-dimensional. And so for the for the 4-dimensional construction, we're not really gonna use the sort of group theory structure, but we're gonna think of primary operators, which are essentially quantization of the Boston modes that I just showed. Now, there are many ways to motivate that. I guess my sort of main motivation was the relation to twistor theory, but there are many sort of aspects in which this construction emerges. The twistor theory motivation is as follows. So twistor space is essentially, it's a fiber bundle. So locally, you would think of this as the celestial sphere in terms of lambda. You can use your sort of inhomogeneous coordinate set, the 2D coordinate, and each of the sets is fiber with a C2. So this C2 is essentially the coordinates mu alpha, where alpha is 1 or 2 or plus or minus. So locally, there's this twistor space here, and what we want to think of, what we want to think is about sections in this twistor space. So these are essentially mu alphas that depend on set. So this is one way to motivate the fields that we're going to be talking about. If you sort of quantize the canonical commutation relation, the natural OPE that this field satisfies is this one. And there is a very simple OPE between the graviton and the Goston mode that's completely equivalent to this one, which actually appeared in this paper by Hinwich et al. And I hope that by the end of this talk, you will see why these two OPEs are completely equivalent. So the sort of global modes of this OPE, if you sort of counter integrate the global modes, you will recover the commutator. So that's exactly what we just discussed. But in general, what you can do is you can start doing OPs with sort of multilinear terms, multilinear operators in mu. So that's sort of the motivation for this, because we know that W is given by sort of multilinear polynomials in mu. Now we have an affine structure where mu's depend on set, so we're going to consider the corresponding operators. So just to start with, we start in this case, in the group theory case, we started with 2 generators which satisfy the Heisenberg algebra. Here we are starting with this OPE, which, as I said, is related to Boston modes. In this case, we consider these wave functions which live in this torus. Here we're going to consider the vertex operators, which are essentially multilinear combinations of mu. We're going to add some momentum generator, and we're going to do normal ordering. So far, these are exactly as in string theory. There's this Beresin formula, which is essentially this module product in the group theory case. If we actually take these vertex operators, we can do OPs very easily using also the Baker-Campbell-Hauser formula. The only difference is that we're going to get this funny pole, because the relation between mu plus and mu minus has this pole rather than a logarithm, as it is in string theory. So there's a question how to deal with this pole, but other than that, it's just plainly vanilla multiplication of vertex operators. All right. So once we take the here in the group theory case, we take the commutator and we kill the identity term. We get the structure constants of SUN. In this case, we're gonna get what we're gonna do is we're gonna take first the sort of leading order in N. So we expand Q, as I said, in terms of just to remind you, it's sort of 4 pi over N. So we take the large N limit, and this approximates to 1 plus 4 pi N and so on.
Yeah, but can I
And yes, please.
just to orient myself, when I think of the gravitational Goldstone modes, I'm familiar with the Himwich paper with like the C mode or like some derivatives of it sometimes. So what are mu plus and mu minus supposed to be relative to each other to be like the C that I think of as like the like late or early U value of the shear?
Oh, that's an excellent question. Yes. So the sort of small modification you have to do is that you have to allow for a central term in H1. So you have the leading graviton being abelian in that paper. If you allow for sort of a central term in the leading graviton of P, which we know from W it has to be there, you sort of can identify C with one of the components of you can identify C with one of the components of mu. Yeah,
Like, I mean, sorry, so can we just count the dimensions here? So like, so I'm fine with basically like, basically I would say there's C and N that are weight delta equals, I guess, -1 spin 0 operators, and their descendants are the radiative guys with one or the other helicity. So what's like the conformal dimension of mu minus or the one that's giving the central term here?
right. Yeah, there's a little subtlety with counting the dimension because you are doing this little group transformation. So what you want to do is essentially you want to interpret them as integer dimensional modes, but for that you need to sort of change the frame by multiplying with omega, which has weight 1/2, 1/2.
Right, that's like with
So
this P that's in the paper by Himwich and others, like the PZ is this guy.
yeah, you can think of, so essentially the P is essentially mu lambda. Yeah, we can think of P as having both of the components of, if we sort of expand lambda in terms of omega 1 z bar, okay, we can just consider z bar instead of that. And so we have like z bar mu minus, mu plus, sorry, this is h. And then P is like the derivative of h, which is, I guess, mu minus in this language.
Okay, thanks.
Okay. So just to go back to where I left, so we have sort of this OP. So this OP is, it comes by expanding Q in the large N limit. And so we notice that the first term here, which is the identity, it won't have a pole, so it doesn't contribute to the OP. So we only keep the term that has a pole, and we get exactly the structural constants that I was mentioning before. The sort of higher poles are suppressed by 1/L corrections, but nevertheless are very curious, and so far I don't really understand them. They seem to point towards a higher spin structure, just because they have higher powers of lambda tilde, so they might actually point towards some richer structure. But so far, leading order in N, what you find is this simple sort of cat-moody OP, where the structure constants are given by the bracket, and the analogy is of course direct. We think of the structure constants essentially being as the delta function that I just mentioned. So there is momentum conservation here. That's part of this sort of contraction here. And the antisymmetry is manifest because this bracket is antisymmetric, and so it actually counts as a SUN or SU infinity structure constant. The compact, sorry. Let me just mention that the compactness of the group is something that is of course lost because here we're dealing with SL2R rather than SUN. Yes.
So if we just compare the levels, it would naively seem like your n is related to like the central charge going to infinity too, because it's like the IR cutoff is in both of those, or would be in the expression if I was just looking at like the level that I'd expected loop order. Is that something that you think is like, like I don't know.
Yeah, you're right. So if you look at just the 2-point function, you know, like in this language, you would have like a 2-point function, which is like the AB1. I mean, of course, this is 0. So far, we're setting this to 0 because we are looking at 3-level amplitudes. But the 2-point function is essentially just you know, the trace of two of these generators, and I think you have to normalize them, or at least in this framework, you have to normalize them by 1/n. And so you have delta function times 1/n. So it depends how you normalize. It depends how you normalize these keys, the operators I have defined here. But I think you're right. I think that essentially 1/n in the sort of putative central charge. It's definitely not there in the sort of positive negative helicity coupling. Like when we write a scalar here, the coupling is essentially just a delta function.
Sure, but we wouldn't expect the off diagonal ones to necessarily.
Yeah. Those ones are those ones when have the central charge. Oh, sorry, the level. But it might very well be that there is a 1/n in the level. It's a good question.
Cool.
All right. So how am I doing in time?
Not great, but it's been interesting. So you can, I don't know if you can wrap up in the next 5 or 10.
Yeah, definitely. I was just asking if I should wrap up right now or so how much what does not great mean?
Well, let's not get into that right now. Yeah, in the next 5 or 10 minutes would be good.
Okay. So what follows is just comments. So I'm not gonna go much into any other detail. I acknowledge that you might have been suffering in the last 10 or 15 minutes with group theory and all that. So I won't make it any more technical. Although there are many technical aspects of course, they are very important to discuss, and you know, half of them I haven't really figured out so far. So just to sort of give you some closing remarks, there is a very simple way in which we can relate the OPE that we has derived from these group theory considerations to sort of soft theorem, which is just the fact that here lambdas are generic in energy, and so you can think of doing energy expansion even though you don't need to. But if you want to see sort of the hierarchy of subcurrents, you might as well do a expansion in terms of lambda 1, say. So you can essentially rewrite this, for instance, as a shift. The shift is nothing but if you look at the collinear limit, this shift is essentially just the angular momentum. So you're taking the sort of leading graviton theorem and supplementing it with angular momentum generators, which of course are expected to appear as you go higher and higher orders in energy. So that's totally expected. What's nice is, of course, that all this can be resumming to this group theory structure, but that seems to be more general. So of course, when you have this angular momentum, it's very tempting to relate that to the massive case, because the angular momentum operator would act indistinctly in the massless or in the massive case. So we can as well write a similar looking OPE, where also we exponentiate the massive operator, angular momentum operator, and that's related to black holes being essentially described by massive primaries. And that's a very, very nice story, but I won't have the time to cover that. Although let me just say that at least classically you would essentially replace this angular momentum operator by a spin vector, which is exactly what you would expect for a black hole to be parameterized in. So that's all in the sort of realm of the soft theorem and the sort of multiple expansion. To make it a little more precise, we can essentially write a correlation function of multiple Kac-Moody currents. Sorry, here you should think of insertions of rather Kac-Moody currents. You should think of insertions of other sort of primary fields. Of course, because there's no level between Kac-Moody currents, you won't get a correlation function. But if you add adjoint primary fields, like transforming in the adjoint representation, you will get something non-trivial. In any case, if they transform in the adjoint representation, you can always do a sort of contour integral argument, and you will find that there is a sort of exponential soft theorem where the angular momentum operator has been exponentiated, but you also have additional sort of contact terms. So these contact terms, they can come from the fact that in this contour integral you will have sort of multi-particle singularities and not only collinear singularities, but they can also come from the fact that there is a term at infinity. And so that term at infinity actually is related to momentum conservation in Z, not in Z bar. I won't have time to explain why that term at infinity is related to momentum conservation, but you can check out the paper. But the important point is that in this construction, the sort of anti-chiral part of momentum conservation is straightforward. It's simply the color structure. The other part, which is the constraint on Z, which is the usual problem in the celestial sphere, that there is a very degenerate region in which the operators can live. That actually forces us in this sort of free configurations to include this sort of residues at infinity, because otherwise the sets would still be a free, would still span the whole celestial sphere. So that's a very subtle point, and I'm happy to discuss more. But just to give you like a very general sort of closing remark, we can of course expand now our vertex operators in terms of mu's. These mu's, we can count the SL2R spin. You will find that they have a spin n, but essentially n is equivalent to 1 minus n if we Lie transform, so it has the right way for being W generators. The sort of key points that they are normal order, and so we can do OPs with normal order operators. If we start doing them, very easily we find translations, we find Lorentz transformations, and we find some higher derivative operations which very much resemble conformal transformations. And so this is sort of a covariant way or a color ordered way in which we rewrite the WOPs, where essentially lambdas, which I should put a tilde in, are essentially just sort of simple color combinations. So we can rewrite this, of course, in the usual language if we re-parameterize lambda in terms of omega and Z bar. But then, of course, the expressions start growing, and we have like multiple terms that don't really combine into each other. So at the end of the day, you can just look at the sort of Jacobi identity, or you can just replace this operator by a W. Any of the procedures would land you into this sort of simple SL2R right covariant OPE, where this is just the epsilon tensor of SL2R right. And you can show very easily that this is equivalent to the algebra that was introduced by Strominger in this paper. So of course it consists of an infinite dimension extension of the Poincare group, which acts as a symmetry of the S matrix as long as you include this sort of extra residue term. So actually this one vanishes for the first 3 orders, but it's there very explicitly, and there's a very explicit expression for this term in my paper for higher orders. So nevertheless, the OPs are very much controlled by the symmetry itself. Okay, so just to give you an outlook, I guess, if I haven't done that already, probably I have done it. But yes, let me emphasize that we have derived this sort of kinematic version of the sort of color version of W, starting from quantum group considerations pertaining to deforming SUN at large N. The sort of lore that we want to advocate is that for the kinematics is sort of emergent. So we have seen momentum conservation emerging from color constraints. The classical limit, of course, is very well understood. There are many papers about large N deformations. We want to understand the finite N deformations, and that may have very technical subtleties, as the one pointed out by David, of course. But there are also more sort of intricate structures that appear when you have Moyal quantization rather than simple Poisson brackets. So that would be interesting to explore, maybe pointing towards a quantum deformation of the theory. More from the classical side, we know that W generators, of course, are realized in terms of asymptotic charges, so we can conserve quantities from them. So it's also something that's not, it has phenomenological implications, so we can use them to evaluate, generalized memory effects and so on. And it would be interesting to address them from the color perspective. So I guess that's all I wanted to say.
Questions? Going once? Going twice? Sold. Well, I guess Alfredo had plenty of questions during the talk, so let's thank him again.
All right.